Hello there guys, welcome back to another inexorable maths video. In this video I'm going to derive or prove this relationship here. So these are moment generating functions. We've got the moment generating function of a linear function of a random variable. So alpha and beta are numbers or constants, real numbers, and x is a random variable. And when you take the moment generating function with respect to that random variable, you actually end up getting this relationship here. I will make a quick comment at the end on why this is useful, but just trust me, it's useful. Let's go straight into the derivation. First thing we should do is remind ourselves the definition of the moment generating function. The definition of a moment generating function is this. It's the expected value of e to the power of t times the random variable. That's literally what it is. So let's start with the left-hand side of our what we're trying to prove here and see what happens when we do that. So the moment generating function of alpha x plus beta of t is equal to the expected value of e to the power of t times the whole random variable, which is now alpha x plus beta. And then we can just use some index laws here. So we've got e to the power of t alpha x times e to the power of t beta. E to the power of t times beta is a constant because it doesn't have an x in it. It does not depend on the random variable, so we can take it outside of the expectation like this. We've got e to the power of t alpha x. And the last step is to just think about, it's just how you kind of split the t alpha and x timesing together. So what I'm going to do, because you might say, wait a second, isn't this going to be the moment generating function with respect to like alpha x of t? You could think of it like that, but all we have to do is say that t alpha is its own, this is a variable, not a random variable, but it's its own variable. So you can see if I put the brackets there, then this expectation is m sub x of alpha t rather than m sub alpha x of t. So it's just the way that I'm thinking about it. And so what I get is just that. So I don't need to keep writing it because I can literally just directly replace that. So what I have is e to the power of t beta times m sub x of alpha t, and that's the result. So it's actually very, very, very simple to prove. This is a separate thing up here, that this is just the definition, so it's not actually part of the proof, but that's the idea. Now, why would anyone want to do this? Well, let me give you a quick example. So let's say that you would like to find, and this is going to be the next video on moment generating functions, you'd like to find the moment generating function of, let's say, a normal distribution. So I want the moment generating function. I know that the moment generating function for a continuous random variable is the integral from minus infinity to infinity of e to the power of t times x times the probability density function if it's a continuous random variable. Let's say that I'm trying to find the moment generating function of a normal random variable. Then I've got to do the probability mass function or probability density function of a normal random variable, and that is really, 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 really annoying to integrate because it looks like this. And I'm still writing, and I'm still writing, and I'm still writing. There we go. So the question is, do I want to do this integral? I probably do not want to do this integral, right? I do not want to. So what I can do, and again, I'm going to fully do this in the next video, so leave a link in the description for it. But what I can do is I can consider z, and z is of course a normal distribution, the standard normal distribution, mean of 0, variance of 1. I can consider this and I can find the moment generating function of this guy. And this is super easy because it's the integral from minus infinity to infinity of e to the power of t times x times, it would just be 1 over the square root of 2 pi times e to the power of minus a half x squared, like that. Because this is the probability density function for a standard normal distribution. Now, I'm not saying this is easy peasy, but you can see that this integral is significantly easier than this integral. And if you remember that any standard normal distribution can be mapped back onto whatever normal distribution that you want by using a linear function, then you can basically find the moment generating function of any normal distribution. Remember, there's this expression, this formula, z is x minus mu over sigma. That means that z times sigma is x minus mu, and that means that x is just z times sigma plus mu. Or if you prefer, I'm going to write these the other way around. So sigma times z. So now this is in the form alpha times a random variable plus beta. And so all I need to do here is just use my formula. So once I've found the moment generating function for the standard normal distribution, I can just use the formula that we've derived in this video to find the moment generating function for any normal distribution. And it saves me having to do a ridiculously annoying integral. So that's just one of many examples of why you would actually care about using this formula. So it's super important to understand and know. It's not just one of those ones where it's like, this is just a nice result. No, it's super useful. So I'd recommend making sure you're super happy with it. But that's everything I've got to say about this. Stay tuned for more videos on the moment generating function, and I'll see you in the next one. Cheers.